Hello. Hello, everybody. My name is Li Jun from China, and my talk is about automotive intrusion detection. So, firstly, allow me to introduce myself. I'm a security researcher from Qihu 360, and I have been started to repairing cars when I was 15. So I know something about the car. And after I graduated from the university and I worked as an information security researcher, so I think it's my privilege to combine my experience in cars and my experience in information security. Sorry. Okay. And nowadays, I'm mainly focused on the security of embedded devices, and currently I'm researching on automotive intrusion detection, which is a serious threat that may threaten the driver's life. So the outline of my talk will be a quick recap of the status quo of connected vehicle security research. And in this part, where I will talk about a few automotive working principle and the hacking incident. And then I will talk about CANBUS anomaly detection, which is my work. Okay, this is our future intelligent transportation system in which all the vehicles are connected via various communication methods. You have DSRC, dedicated short-range communication for the communication between cars and the roadside unit. And then you have cellular connection for the cars to communicate to the internet. And then you have the apps, your mobile phone, or in the future, your mobile phone and your computer, you can also interact with your cars. With your car. So this is what will be like. The cars on the road are coordinated to increase the efficiency of the transportation system. And this is a timeline of car security research. From the start, they are just doing some research, like the reverse engineering the controller firmware to modify the performance of their car. And then the research on the immobilizers, they want to steal the car. So the crypto used in the car key fob has been cracked. And then remote attack via the OBD interface. OBD is onboard diagnostics interface, which means the mechanic use their dedicated tool to communicate with the internal network of a vehicle. On the network, there are different control modules for the engine and transmission, etc. And then there are research about the remote control features of the connected vehicle. For example, those vehicle can be controlled via a mobile phone. You can use your phone to open the door to authorize somebody to drive your car. And then I think last year, Charlie Miller and Chris Valasek published their research on the Grand Cherokee, in which they could remotely control the steering and brake of the car. So this is a significant change, I think, that before this, the security research doesn't threaten the life of the driver and the passengers, but from then on, the vulnerability would threaten the driver's life. I don't know if you guys can understand my English, right? So what's the in order to control the physical feature of the cars is to inject CAN packets. CAN is a network protocol used to network the different ECU. What is ECU? I will talk about later. To connect the ECUs, and the connections are often not encrypted or authenticated. So, this is a presentation that Charlie Miller will give at this year's Black Hat. They will talk about the idea I want to make sure is that car hacking will become easier and easier. So there are many tools will be released. For example, the CAN protocol analyzer and the open source software used to analyze this traffic. So car hacking will be pervasive and will attract more attention of the hackers. So let's see an example of the Jeep hack. How did they get into the controller network of the vehicle? The vehicle has a network that network the ECUs together, and then it has an infotainment system which contains a Wi-Fi module. So the attacker used the Wi-Fi. The Wi-Fi's password is generated from a random seed, and the generation algorithm has a vulnerability, so they could calculate if you know when you first started this car, that is to say if he knows when you generate the password, he could calculate the password himself, so he could get into the Wi-Fi, and then through Wi-Fi, he found vulnerabilities in the infotainment system, so that allowed them to access the CANBUS. Then they extended the range by using a rogue base station like the femtocell, compromised femtocell. They could use that to extend the range to remotely control the car, I think, from 100 meters away. And then they discovered that if you use a mobile phone that connected to the Sprint network operator, you could extend this attack internet-wide. And then the threats that will face the future autonomous vehicle is sensor security. Autonomous vehicle will have various sensors mounted on them. For example, LiDAR, GPS, and the ultrasonic sensors. But these sensors are easy to spoof or interfere. The GPS signal, as you have known that from my Konix talk, the GPS signal can be spoofed. And the ultrasonic sensor also can be spoofed. And last year's Black Hat also said that the LiDAR is also susceptible to spoofing. And then this is the LiDAR attack I talked about. Now I will talk a little about the working principle of modern cars. A typical car consists of there's 4 main subsystems. You have body electronics, controls your instrument cluster, remote keyless entry. That is the security I talked about, the immobilized security. And then you have powertrain hybrid. That part is what caused the remote control of their physical features, because they introduced, I will talk about X-by-wire systems. And then you have infotainment and communication system. This is the main attack vectors for the hackers, because this system often features Wi-Fi, Bluetooth, cellular networks, etc. Then you have the safety and driver assistance. That part is like the autonomous car the threads are facing the autonomous car, you have various sensors to sense the environment and to control the car. For example, the adaptive cruise control uses radar to detect the distance between the car in front of it, and to control the engine, thus to control the speed. Okay, this figure shows that what the powertrain consists of. You have engine, you have transmission, and you have brake system, and you have steering system. Next, I will talk about the X-by-wire system. You can see that the difference is in the transmission, steering, and the engine control system, because the traditional car don't have the X-by-wire features. So the hacker, if he gains control over the CANbus, he still cannot control the physical features. Okay, I have mentioned the ECU multiple times, so here I will explain what an ECU is. This is from Wikipedia. I think it's pretty accurate. An ECU is just a generic term for the embedded controller, I think, in the cars. It takes the sensor input or the driver's input, like the acceleration pedal, and then output signals to control the actuators to control the modules, that's the car. Okay, here is an example of engine control unit. It takes as input multiple signals, like the ignition switch, throttle position sensor, and the manifold air pressure sensor. Actually, my research later I will show that on CANbus anomaly detection is based on the parameters, the interrelationship between the parameters. And then the output is the actuators. For example, the actuators often are servo motors, and I think valves, and the fuel pump, etc. So let's look at a more vivid example. On the lower left corner is the driver's acceleration pedal, and this pedal, when the driver presses the pedal, the signal is collected by the engine control unit. Notice that the engine control unit, the abbreviation for electronic control unit and engine control unit are the same, but you have to base your interpret it based on the context. And you have the sensors to monitor the driver's input. You have the speed input to the engine control unit. You have the ignition switch, etc. And then the ECU output signal to control the actuators, like the fuel pump, like the regulator, the generator, etc. So ECU is just like the system is like a closed loop control system. This is from the ECU level, but as I later will talk about, the whole car can be controlled and can be seen as a closed loop control system. Okay, this is the automotive as a whole. You can see, I talked about the engine control unit, but as a car, from a higher level, you can see that a car takes as its input the environmental data. For example, the distance between the cars in front of it, the current speed, and nowadays the height precision map, for example, and then output is the actuators. It's like the ECU, but you can see the automotive. Because automotive has many electronic control units. They are networked together. So when you visit this entity as a whole, you can deem it as a closed loop control system. And now I will talk about the drive-by-wire system. What is drive-by-wire system? Drive-by-wire means it's controlled by electric wire. This on the left is the traditional drive-by-wire system. Traditional throttle control system. The driver press on the acceleration pedal, and then this is mechanically connected to the throttle body. So it's safe from the cybersecurity perspective. And this features a cable, but it's still mechanical connection in the middle one. On the right, we have what is called drive-by-wire system. Drive-by-wire system. The EC in throttle control module takes in as its input the acceleration pedal. The acceleration pedal is just a sensor. It could be a potentiometer. And then this signal is processed by the EC in, and then the ECM output is signal to control the servo motor to control the throttle. Why they would change it from that to this? It's because humans are prone to error. So if you use this system, you could you could control the throttle in a more efficient way, I think. And above all, they want to control the speed via the electronic control system. For example, the autonomous car, you have to be able to control the throttle by electronic system. I don't know if that makes sense. Okay, that's why the drive-by-wire system introduced the cyber-physical threat. The throttle control module is often integrated with the engine control unit, and the engine control unit is on the CANbus, the controller network, and the infotainment system, which has Wi-Fi, Bluetooth, is also on the CANbus. So there is a danger that if an attacker can via the multimedia, the infotainment system to control the engine control unit. And as I said, engine control unit takes many input, and those input is transmitted on the CANbus by other ECUs, for example, the transmission ECU. And the steer-by-wire is also the same. On the left, we have a traditional steering system. Note the steering wheel is mechanically connected via the universal joint with the wheels, so it is not hackable. On the right, it is a steer-by-wire system. In this system, the steering wheel is not directly connected to the wheel. Actually, the steering wheel is just a sensor. It is also, just like the drive-by-wire system, the sensor gives the signal to the ECU, and the ECU then output signals to control the servo motor to control the steering angle of the car. This ECU is also on the CANbus. Okay, this is what I said. To view the vehicle as a whole, a closed-loop control system. You have for example, user variable, which might be the steering wheel angle and the user's press on the acceleration pedal. Okay. I mentioned that the engine control system has an ECU, the transmission system has an ECU, but in fact, in order to do some certain tasks like the adaptive cruise control, this ECU have to collaborate. So in order to enable the collaboration, we have to introduce a network to enable the communication between those ECU. The CANbus is why CANbus is used. Okay. This is a more general network architecture of a car. You have this many protocols. For example, the most media-oriented system transmit, I think, is for the infotainment system to transmit high bandwidth multimedia data. and you have the different CANbus. They are I think they are working at different data rate, so they are connected via by a gateway. So you see that infotainment system is on the most network, and the infotainment system have Wi-Fi, cellular, Bluetooth. Notice that. I think the attacker often goes through the wireless connection, and then gateway and the drive CAN. The drive CAN is where the engine and the transmission control module is on. Okay, this is important. Let me explain it once again. CANbus is used to network the engine, transmission, and all the safety critical systems. So let me give you an example of how the vehicle communication system works. This example is, I use speed as an example to tell you that how the speed as a parameter is shared between these different modules. First, the electronic stability program calculates the current speed from the data that from the sensor data that the sensor is mounted on the wheels, so it could calculate the current speed, and then it transmits the speed on the CANbus. Notice the red line. When it sends this data, the CANbus is a broadcast network. The speed, if the ESP control module sends out the speed, all the modules on the CAN network can receive that. And you see that the engine management unit, also called engine control unit, can receive this speed. Why does it need this parameter? It needs this parameter to control the torque output. Because, for example, when you are in an adaptive cruise control model, the engine have to know the current speed in order to control the torque output to control the speed, right? And then transmission control unit, it depends on the current speed to calculate which gear it should be used. And then the adaptive cruise control system received the speed, and then this system calculates from the speed. He can decide how long the distance it should keep from the car in front of it. So this is how CANbus works. And then through the gateway, the speedometer can receive the speed and display the speed. And the seat controller and the infotainment system also will receive the speed when it will turn the volume, the infotainment system's volume up when the speed is high, because the noise will be high too. And the inertial navigation system also needs the current speed to calculate the position. Now, in the CANbus, okay, I think this is the meat of this talk. CANbus signaling. The CANbus is just two wire. It uses differential signaling. It is used because it has very good anti-interference characteristics. The bus is very good at anti-interference. Because it's not very important. I just skip that. And the bus uses the difference between the two wires to decide whether it is 1 or 0, the signal. So it's very good at, for example, the common mode interference would be not interfere this bus. Now, the CANbus, okay, the frame structure. The CANBUS doesn't have, the CAN data frame doesn't have the original or recipient address. It just has a message ID. So if a malicious packet is detected on the network, you cannot simply trace back who have sent this malicious packet because it has no originating address. So and its payload is often 8 bytes per packet, and there are many higher layer protocols that based on CANBUS, but it's not for me. I don't consider that because the parameters I use, the speed, the gear ratio, these parameters are carried in a single packet. So the higher layer that which has a packet segmentation, the data segmentation and reassembly, I don't consider that. Now, I mentioned that the CAN only has a message ID. The message ID is also used as a privilege field. It uses this value to decide who, if two ECUs want to send the packet simultaneously, it uses this to decide who got the access of the bus. So if an attacker got on the network, he can simply launch a DDoS attack, declare of service attack by sending packets with the highest priority. For example, with the ID 0. Now the difficulty of CANBUS defense. Now real-time requirement. The data is real-time data. For example, the speed is real-time data. If you do some process on it and introduce extra delay, it may interfere the normal operation of the system. And hard to trace back to the sender because it has no originating address. High cost of false positive because you see all these ECUs are controlling safety critical functions. If you for example, if you detect there is a false positive and you cut off the communication of the ECU, it might cause severe problem than not to. Okay, the attack type, and apart from the attack declares of service attack I mentioned earlier, there are mainly two types of attack that targeting CANBUS: packet injection, parameter spoofing. For example, the Jeep pack, the car only allows you to control the steering system when the car is traveling at below 5 miles per hour. So if an attacker wants to control the car's steering system at high speed, he might have to spoof the speed. So what I'm doing is to detect this kind of attack. So you can see that this year's Black Hat will be, there will be a talk about advanced CAN injection techniques. That you can see that there are certain prerequisites for the attackers to control the physical features. So let's wait and see if my method can detect that kind of attack. And then I will talk about others research on the CAN anomaly detection. I will also talk about what the industry have been doing to prevent car hacking. Next, the SAE is, I think it's Society of Automotive Engineering in the United States. They have published recommendations to develop safe vehicle system, cybersecurity systems. So they have also mentioned intrusion detection solutions. They have mentioned that you have to do some research on it. And some folks have started companies to specialize in Automotive cybersecurity, if you don't know that. There's the Argus is, I think, is an Israel-based company that specializes in car security, and this is an American-based visual threat. Yeah, it's also specialized in car security. Okay, this is the original architecture I come up with in order to defend the CANBUS from CANBUS. I tried to add communication control gateway at each ECU, so that if one ECU is misbehaving, I could cut off the communication to kick it off from the CAN network. But later I realized this architecture is good, but it's very hard to implement and very expensive to implement. Okay, this is the same architecture, but it's more concise. Even if we adopt this architecture, we are still faced with the same problem of false positive detection cost. And the packet's origin tracking. Regarding the packet's origin tracking problem, somebody said they can tell from the CAN message ID to tell who have sent those messages. But I think this makes sense only in a normal system, because in a normal system, which ECU send what parameters is predetermined. For example, the electronics stability control program send the speed. So the speed is wrong, you can tell that you can tell that the speed is sent by that ECU. But in a malicious packet network, each node can send any packets with any ID, so it's not good. So I think I would use this architecture. This is the CANBUS. We can't control the communication of these ECUs, these modules, but we could use an IDS to detect if there is something wrong on the network, and then we use the result of the IDS to control. If we detect an attack, we use this to control the wireless gateway, to control the infotainment system. We cut off all the wireless communication and fire an alarm. And this is kind of like makes the car fall back to a safe mode without any internet connection. Okay, this one is more vivid, I think. Okay, this is research by Daimler. They also done some research. Also have done some research on the CANBUS anomaly detection, but they use the introvate because a car on the car system is not as complex as the computer network, because all the data is the data on the network is all those parameters, and those parameters are I think can characterize the car's status, and the car's status is limited, very limited. So you could build a model to detect the attack, and they use entropy-based anomaly detection. I just want to mention that I don't judge if their work is good or bad. And they injected four packets, four data points, and they detect 3 of them. And the remaining one that they didn't detect, I think it's because it's not deviated too far from the normal value. Okay, my method, build a mathematical model of the car. And this is the same as to bundle those parameters together. For example, I can tell if the speed is normal or not normal by using other parameters. For example, the RPM, the engine rotational speed, and the gear, current gear. I use these 2 parameters to detect if the speed is wrong. So it would be somebody will tell me that the speed and the RPM and gear, their relationship can be described using this simple linear equation, right? You have the rotational speed to that output from that is the output from the engine, and the gear ratio. You multiply the gear ratio, and the powertrain also has their the gears. So you have to multiply constant. Does that make sense? Actually, this won't work because this is car transmission system. This is where the RPM and the output is connected to the wheel. It has many clutches. I don't know if anybody understands what is clutches. It controls the output of the torque. So these clutches will introduce some nonlinearity. So the linear equation I just mentioned is not sufficient to describe how the system works. Okay, it's not linear. Okay, so what to do? So I also want to mention that the speed has many characteristics that can be used to say if it is anomalous or normal. For example, the speed is a continuous variable. You can measure that if it is continuous. To measure that, it's very simple. And the change rate, the acceleration and the deceleration also have its limit, because now only the top sports car can accelerate from 0 miles per hour to 100 miles per hour in 3 seconds. So does that make sense? Okay. Now, I just want to use this figure to show you that the many parameters are related to each other. For example, this line, this I think is the purple one, is the acceleration pedal, the driver's input. And you can see that the driver presses on the acceleration pedal, and these are throttle and air flow rate and speed RPM. They will go up with the acceleration pedal. But does that same can be described using a simple linear equation? Of course not. So what do we do to build the model to describe this relationship? Okay, we used machine learning. But before we get to the machine learning part, I just want to say that how would we use this model? You got the, for example, now let's assume that we have already built a system model, okay? And then we use the live data stream and extract the parameters, for example, the speed, gear, RPM, and then we use this data to make a prediction via this system model, and then we use the prediction. For example, I use the current gear, current RPM, current acceleration pedal value. I use those values to predict the current speed. And then I use this predicted speed to compare with the actual speed I received on the network. If there are too much difference, the predicted value is deviate too much from the actually received value, I deem that as an attack. I think that speed has been spoofed. And we can also use all the parameters to make a prediction of all the parameters. Now, I use this set of parameters received on the network to make a prediction of all the parameters, because this system is trained or created from the normal data. So if that set of data is anomalous, it's not, when the system makes the prediction, it will not be the same. So it will deviate very much from that input. So by comparing them, we could tell if it is an attack. Okay, let me tell you what is machine learning. Actually, this is deep learning. I will use, because we used the neural network. What is a neural? Okay, a neural is, this whole system is neural. You have this input, x1 through xn. That is an input vector. And then every input, you multiply it by a weight. And then this sum, then we sum the weight together and use this to go through a transfer function. The transfer function is often a nonlinear function. So I think this is where the nonlinear characteristic is described. Because remember that the linear equation cannot describe the system, but here we have the nonlinear unit. Because by using sufficient training data, I think we could model this system. Okay, this is a neural network that has many neurons. So actually, we used a neural network just exactly like this. We have an input layer and a hidden layer and an output layer, only 3 layers. And I will publish the code later. You could tweak it yourself. Okay, let me show you how a neural net works by go to this website. Okay. Okay, this is the website that created by the machine learning experts. You can see that this is a neural network. You can configure the network you want to do certain tasks. For example, I will use this model to do a classification task on that data. So I click on Start. Okay, you can see this network can classify the data set I think, perfectly. And you can see that, okay, I think I will stop here because the deep learning is a very complex subject. I just want to give you the basic idea how this works. Actually, we use this network differently. We use the normal data to train the network. I think I used about 80 minutes of driving data to train a neural network. And you can see these lines are thicker than those because how to explain that, I think. Okay. I just tell you how the training process, what it's like. Okay, I showed you the neural network I used in the PowerPoint slide. That the training process is like just use a template mathematical model, and then you use the training data to adjust the weights and the network neurons to model the system. So it's kind of like create a mathematical model from the training data. And how the training data, how they learn, how they adjust the weights is just the machine learning problem. So let's see the result. Okay, I mentioned that this is a neural network, and I also mentioned that a neural, their input, this vector, it has a weight. So the training process is like just adjust these weights, and then until the system, until the output and the input vector is, I think it's very close to the training data. Okay, this is the car we used to do the experiment. This car has many cyber-physics features, the X-by-wire features I mentioned. For example, it has electronic brake. The brake can be controlled by the electronic system, and the steering, electronic throttle, and the cellular connection, cloud service, Bluetooth key. You could use a cell phone to open the car and to control it. You could use a mobile phone to remotely open the car for your friends. And you also have cellular connections to update the software or the like. Okay, let me show you the cyber physics. Oh, I'll mention that I'm currently collecting data from the engine control CANbus. Okay, this video is just to show you that this car has the X-by-wire system. Oh, sorry. It's just two wires, two twisted wires to connect to the CANbus, and using a CAN interface and the software, you can collect the CAN data. Okay, you see there's no driver in that car. Okay. Okay. The car has drive-by-wire features, and you also can control the steering via the electronic system. So that's why we bought it. We didn't buy it because it looks nice or. Okay, let's continue. Okay, this is the network architecture of the car we used to do the experiment. It has multiple CANbus, but we acquired the data from the engine CANbus because the engine CANbus has the ECM, engine control module, and the TCM, transmission control module. So, now, this is what the CAN database like. I mentioned that the CANbus have a message ID, and the message ID actually says what the payload contains. For example, you can tell from the ID that the ID 10D hexadecimal value, it carries in its payload the status of the front door, right door, left door. But all this database, all this, you have to reverse engineer yourself because this is kept, I think, highly confidential to the manufacturers. So I have spent a lot of time doing that. Okay. Okay, I'll show you the live data stream, what it looks like. You can see that I got the CAN database, I reverse engineered the CAN database, and I attach the database to a CAN analyzer. You can see the instrument status lights. Okay, we got that. and I got those states. This automatically is shown on the software in software. Now build the system. Build the system actually have 5 steps. Data acquisition, which I have shown to you, and the data pre-process, which I will publish the code later, and the data analysis. Because I have a little automotive background, so I know what kind of data is related to each other. So I just chose, I think, 7 parameters myself, and then that's feature selection and model training and testing. So the model training process is just you feed it with the training data which you have been pre-processed, and then actually I trained this model on a server. So this is the data acquisition setup, and this is the CAN database reverse engineer. Okay, this is the CAN data log output of the CAN analyzer. So everything I do is based on this log. So the data process script takes this log as its input, and then output a table of data. Okay, the data has to go through these 3 steps to. Okay, normalization, interpolation, sampling. I think that's don't need to be explained. I think it's very simple. And this is the normalization. But I think I had a few pitfalls at this, because when I normalize the data, I calculate all this data, calculate the maximum and the minimum values from the data set. But notice that, for example, the speed. This training data set may have a maximum speed of 70 miles per hour, and you use that maximum to normalize the data. But later, if you want to test the model, the test data has a higher maximum speed value of like 80 miles per hour. So the model is just doesn't work. So make sure to use the accurate maximum value and minimum value. Okay, the CANbus is a serial bus, so the data is coming in series. So if you want to know at time t all these parameters value, we have to interpolate. So the black point is the actual value I received on the CANbus, and the red ones are the interpolated value. And subsampling, of course, this is very easy to understand because we interpolate so many values, and these values are just don't necessary. So you can see that over a long period of time, the value just doesn't change. So I subsampled it. Okay. This is the result of subsampling. You can see the data is started to change over time. Okay, this figure is actually very important because I said that we want to use the past data to predict the data. So, but how many past data do we use to? So, I used I think 10 data points from the past to predict the value of Why is this? Let me explain it using this figure. It would be more accurate to use this period to predict this point than use just a point at this time to predict the next point. Does that make sense? Okay. So that is why we chose 70 data points as input vector, because we want to include the temporal features of these parameters. Okay, I will publish code and the CAN traffic data. So this is the result. We just take speed as an example to show you the result. I think the blue one, the blue curve is the speed we predicted, and the purple one, the pink one, okay, is the value, real value. You can see it is pretty, I think, pretty good. And then this is the mean square error. I calculated mean square error on 10 data points. And you can see the pretty, I think it's pretty small. And then now let's test its attack traffic. This is this data set is the RPM has been spoofed. You can see that. Okay. You can see that blue area under the curve at the top left corner. I zoomed this in a little bit. You can see that it's not because they are originate the legitimate node is sending the data and the attacker is also sending the data. So I think that's why the curve is not like it's oscillation. Okay, this is attack traffic and the attack traffic. Okay, the result is like okay, the mean square error over the 10 the consecutive 10 data points is the above curve. You can see that under this we have this attack traffic. You can see that we can pretty accurately detect this attack, because when there is attack, the deviation is very large. So if we set a threshold, we could detect the attack. Okay, this is McAfee and Intel. They published the white paper. So in their white paper, they also mentioned anomaly detection, and they said that if you detect an anomaly, maybe you fall back to a safe mode. That is what they said, and I think the idea is quite identical to mine. And this is the people I want to thank. Okay. Okay. The contents I presented is are not all my. I didn't do them myself. So all by myself. So I will include the references in the slides. So if you are interested in cache security, you can read all those papers. Okay, I think we still have 2 minutes for questions.
Questions?
Thank you very much for the presentation. Do we have any questions? All right, thank you very much.
Okay.